Okay, so as I have told you, today we're going to see the problems in Bpsk. Okay, so this is the question that is asked in 2012. Okay, so the question start like this. So a Bpsk scheme operating over an AWGN channel with noise spectral density. Okay, so we got two signals that is given. Okay, so signal 1 and signal 2 both are in different phases. As you can see, it is in plus, and here you got a minus. So if you remember the constellation diagram for Bpsk, one will be ranges in this, that is 0° origin. Phi will be in phi 1 of t will be in 0°, and another logic 0 will be placed in minus phi 1 of t. Okay, so in Bpsk, as you can see, we got two signals, so that is stated in here like S1 of t and S2 of t, and with over the interval, it's an orthogonal signal. That's why they have given with an interval limit 0 to t time period. It's not infinity, so the signal will flows through a time limit from 0 to t. It's not beyond it, so it's not beyond plus infinity or minus infinity. It is a bounded signal. Okay, that's why they have given with a limit. And if the local oscillator in a coherent receiver is 45° ahead, so along with the signal, we're going to add up 45° and we're going to calculate the probability of error. And the function, as you can see, they have given 4 options in here. So out of this option, we're going to see which is the correct one. Okay. So in the coherent Bpsk system, the pair of signal S1 of t and S2 of t are used to represent binary logic 1 and logic 0. So this is for logic 1 and this is for logic 0. Okay, so we got two signals. And next point is S1 of t is already given in the question and S2 of t is already given in the question with the time period of 0 to t in here. And the energy for the transmitting signal is EB or E. Okay. So the normal local oscillator function can be taken with the help of phi 1 of t, that is root 2 by t. This is the carrier frequency. So root 2 by t sine omega ct, and that is also limited to 0 to t. And second signal should be 45° ahead. So along with the local oscillator carrier, we have to add up 45°. So we'll take this data. In here only you have to add up 5, the changes that you want to do, because the first term is represent the amplitude and the second term 2 per omega ct. If you're going to expand it, here you got a frequency component. If you're going to add up some phase, that is called phase component. So the basic characteristic of a wave are amplitude, frequency and phase, right? So here you got amplitude term, frequency term and phase term. Okay, so these are the given data that is in the question that we have taken. So now we'll start to work it on the problem. So the coordinates, it's an orthogonal signal, so that's why it is bounded to limit. So the signal ranges from 0 to t. So that's why we have made an integration in here, and we're going to make a modulated data for a signal 1 and the carrier frequency S1 of t and phi 1 of t. So these are the given data that we have picked out from the given question. Okay, so as you can see, this is the modified data 45° that you have to take, and here you got S1 of t. Just multiply and integrate it. Once we have integrated, you'll get the final value, only DC value alone you'll get as an output. So harmonic terms, that just like 2 omega ct, once you expanding this equation means that will be filtered out. So only the DC component out of this equation alone will take it. So this is for the region 1 value. So we can divide the Bpsk into two regions. So it is region 2 and it is region 1. So region 1 value will be root E2. Similarly, region 2 value also will be same, that is minus side in a constellation diagram. So this is the positive and this one will be the negative. So here you got root E by 2 energy, here you got minus root E by 2. Okay. So next step is, as you can see, with respect to this diagram, here we have finish the constellation diagram for it. Okay, so now our aim is we have to calculate probability of error, right? So the problem for the equation for probability of error, just I have posted in here. So now there are two messages, S11 and S21. Okay, so because we got two regions, right? S11 region, S21. So as you can see, the error at the receiver will be taken it as, if yes, we got two cases. So S1 is transmitted and S21 is received. And another case will be S21 will be transmitted, S11 will be received. So first we'll solve the case 1. So S21 is received while you are transmitting S11 signal. And the region is from 0 to x, and x can be written in terms of probability as the original signal along with noise. So x is equal to root e by 2 plus n. So with respect to the bounded region that we have to write, so we can change the symbol as n less than minus noise should be less than minus your original signal. Okay, so as the result, the distribution for both the data will along with the noise will be just like this. So if you take a normal signal, this will be the Gaussian waveform. So if error is occurred, means as you can see, there is a connection between those two waveforms, right? So this is called probability of error. That only we're going to calculate it. So how we can calculate means, as you can see, the mean of equation can Gaussian distribution is root e by 2. Variance will be n naught by 2. Okay. So, and probability distribution function equation we already know. PDF equation is normally how you will write PDF equation is Px of, in mathematics and all you would have studied. Px of x is equal to 1 by sigma root 2 pi into e power minus x minus mu square, that is mean square by 2 sigma square, right? So this is the standard PDF formula, probability density function formula, the same formula that we're going to use. Instead of mu mean, here you got root e by 2, instead of variance the value is n naught by 2. So expand this equation, and as you can see, 2 and 2 will get cancelled in here. Remaining equation will be only pi into n naught. And here also 2 and 2 will get cancelled, remaining equation that we have written. So after this we're going to take only the bracket, within the bracket terms, into t. Okay, so as the result we can differentiate it. So the final value in terms of x, all the terms that we're going to change it as t. So as a result you will get this equation in terms of t. Okay, so where q is the error function. Okay, so from this diagram actually you can infer the data. Okay, so S11 is transmitted, case 1 alone. Okay, we have seen so far in case 1 we got a quantity error function just like this. So this is for the case 1. So this is the data error function that we got. Now we're going to solve it for case 2. Okay, so as you can see, for case 2, once we transmit, you'll get the same equation. So to get the average probability error, you have to sum up with respect to 2. Okay, average that we have to find. So q of root e by n naught, as you can see, the final answer will be this. Okay. So now we'll see the next problem that is asked in 2003. So at a given probability of error, a binary Fsk, coherent Fsk, coherent means in last class itself I have told you, whatever the carrier that are using at the transmitter side, the same carrier that we have to use at the receiver side as well. So for first, as you can read the question, at a given probability of error, binary coherent Fsk inferior to binary Psk. So as you can see, first technique is Fsk, after that only Psk is evolved. And how this Psk that we are saying, it is as a standard method when compared to Fsk, that we have to say. In terms of frequency means in terms of dB only we will measure it. As you can see, we got 4 options: 6 dB, 3 dB, 2 dB and 0 dB. So how the Fsk is inferior to Psk is inferior to Fsk, that we are going to see in terms of probability of error. So for that you should have to aware about the formulas. Okay, probability of error formula. So this formula slide in first class itself I have showed you for like a comparison. All the digital modulation technique I have posted it. So while you are comparing it, here you got root 2. So root 2 is common. So 1 by root 2 that you have to take. The value for 1 by root 2 is 3 dB in manner. Okay, so that's how. So in a 3 dB only Psk is differs from inferior to Fsk. So the answer will be B in here. Okay. So now we'll see the one more problem in the same here. They have asked it, if S represent the carrier synchronization at the receiver and rho R that represent the bandwidth efficiency, it's rho. Okay, and then the correct statement for coherent PSK they are asking. So first you should aware about what are the terms that are given. Carrier synchronization at the receiver. What does it means is, so we got a transmitter side and receiver side, and in a transmitter we will get a modulator. Here we are talking about PSK. So here the type of modulator is Bpsk. So here one input, that is binary data will be given as input, and second will be the carrier. And once it has been transmitted in a channel, so it will be received at the receiver side, right? So at the receiver side we have to use demodulator. The same carrier has to be used in here. That is the point which is called carrier synchronization. Here we are going to take that same synchronization symbol as S in here. And the bandwidth efficiency, total bandwidth efficiency that we are going to calculate for this communication system. Okay, so and the values are given in here, so that we're going to see now. Okay, so remember the concept for Bpsk, the whatever the carrier that are using, which have to be used at the receiver side as well. It's just like a key. Okay, so obviously now you know S is required. So out of this option, you can directly cancel out C and D. So either it can be A or B. Okay, so anyway, I have already projected in here. Just carefully listen. Now we're going to calculate bandwidth efficiency. And for bandwidth efficiency, the formula is RB by, that is the data bit divided by B, and unit is bits per second per hertz. Okay, so FB by 2B. So FB is that is we in a Bpsk we got two datas. Okay, for a two datas, so it is a single bit. So for a single symbol we'll take 2 bits for a modulation. Okay, so as you can see we'll take FB, sorry, as for a single bit you have to make the variations. Okay, logic 1 means a carrier will be added with a normal frequency, and logic 0 means 180 degree that you have to add up. So data bit is 1 in here, and 1 by 2 that is equal to 0.5 in here. So you can say rho efficiency which is equal to 0.5, and S is also required, which means option A is the correct answer. And one more problem that is asked in 2003 as well. Okay, so we'll see that question. So for a given data, the bandwidth BP of a Bpsk signal and bandwidth B0, okay, of a OOK signal. Here it is the only one ASK based question. That's like comparison for Bpsk and ASK they have asked. Okay, so we'll see that now. So what is the question that they are asking us? They wanted to know about the bandwidth of Bpsk, how it is related with ASK they are asking. Okay, so that we'll see now. So again, with the help of this table, once you summarize all the formulas related to bandwidth, probability of error, it will be easy for you the comparisons. Okay, so this diagram is very important. Okay, so as you can see, we'll take the bandwidth for coherent ASK and FSK, so EPSK, that will take it in here. Once you compare it, both the bandwidths are same, that is 2RB, 2RB, which means you can say the answer will be C. Okay, both bandwidths are same for Bpsk and ASK. Okay, so that's it. That's about Bpsk. So now we'll see the next topic, that is differential phase shift keying. So far in the classes you would have studied the theoretical concept about DPSK, right? So in university, sorry, in a gate point of view, they'll ask you the problems related to it. So far in 2000s they haven't asked. In 90s alone they have asked some problems related to differential phase shift keying. Anyway, you have to be aware about it. So we'll see that DPSK, differential phase shift keying, in now. Okay. Okay. So first we'll see the transmitter structure in here. Okay, so first we got a binary data, and that we're going to take with symbol DT. So based on this transmitter diagram only, we're going to see two problems related to it, that is asked in gate exams. Okay, so we got input binary data, and that we have to process to XOR gate. Okay, so to XOR, as you can see in this diagram, here we got heart of the circuit and here is the XOR. To XOR, we got one input, that is binary, and second input is you have to delay the binary data bit and you have to give it as a second input. Okay, in either way it will work on. So first you will take this and XOR will performs on two outputs, right? So but in an origin position we got only one input, so that will be taken delayed with B of t minus tb and it will be given back to the XOR. So after that you will get D of t and that you have to XOR with B of t minus tb, so you'll get B of t output. So using Bpsk, because Dpsk is an advanced version of Bpsk. Okay, so why we are moved to Bpsk from Dpsk, it's very important point. In 1 mark they'll ask you in gate. So in Bpsk we need a carrier. Okay, a coherent carrier is needed, but if you just look at in transmitter, there is no need for carrier in. Okay, so at the receiver side we'll talk about it. Okay, so here we got a carrier that is used in here, so only this signal alone will be transmitted. So from this signal the receiver will extract message data and carrier. There is no need to separately give the carrier as a second input to the Dpsk transmitter. So Dpsk receiver, once we saw this topic you will get to know. Okay, so there is no need for a coherent carrier. The synchronization of carrier is not needed in Dpsk. Whereas in Bpsk we need to synchronize both carrier and transmitter and receiver as well. Okay, so now we'll see a simple example. We'll take a data bit D of t as this binary data bits 0 0 1 1 in the streams that we have taken, and second input should be the B of t, right? How B of t will be taken means, first bit, remember that you have to take it as a reference bit. Some cases in question they'll give you reference bit take it as 0 or reference bit take it as 1. Then in question they'll inform you. In here we'll solve it with two examples. So first in this example I'll take reference bit as 0 in here. So as you can see, after zeros added, the same data that we have taken. Next what you have to do is phase of B of t that you have to write. 0 means pi, 1 means 0. Okay, so phase of the B of t that we have written in here. And B of t minus tb, how it can be written means the B of t that you have to delay it. 1 bit you have to delay. So as you can see, we are going to delay it. So now you got the delayed data. Next step to get final Dpsk output. Before that, just write the phase of B of t minus tb. So your next step to get the final Dpsk output, what you have to do is, so as you can see in this example, so here you have to XOR both input, that is B of t and B of t minus tb, that you have to XOR. Okay, so that you will get the final output 0 XOR 0, which will give you 0. So in this manner you have to XOR this output to get d dash of t. Okay, so here we have taken, because based on this example only they have asked a question, two questions they have asked. Okay, so as you can see in here, reference bit that we have taken in here is 0. So we'll see if reference bit is 1, what will happen. As you can see in here, we got a binary data, and for reference bit we have taken 1, that you have to XOR it. Sorry, that you have to shift it. Okay, as the result you can get the phase of Dpsk, and Dpsk, once you got it, you have to delay it, and delayed data also you have to write in terms of phase, and to get the final Dpsk output you have to XOR this data, so this data and this data. Once you XOR it, 0 XOR. So here they have performed the operation, not XOR, XNOR they have taken. Okay, so it also very important in question. They'll give you which type of universal gate that you have to use. So we'll see that two types of problems in the following class as well. Okay, so in bit probability of error related question, so far they haven't asked. Anyway, they have given you the formulas probability of error for Dpsk in here. Okay, so now we'll see, just a minute. Okay, the problem that has been asked. Okay, so first 2-mark problem in 1989 they have asked a binary data transmission DPSK is preferred to PSK. So when compared to BPSK, we moved to DPSK. Why? In the sense they have given 4 options. A coherent carrier is not required. Yes, obviously the first option itself we got the correct answer. Whatever the carrier that we are used at the transmitter will not be used at the receiver. As you can see, this is the receiver diagram. Here there is no separate local oscillator is used, because based on the oscillator only you can reproduce that same carrier that is used at the transmitter side. But in here, out of the receiving data, we're going to delay it and we're going to synchronize and demodulate to get the final output. Okay, so and second one is energy given per bit probability of error. No, that is not also correct. 180-degree phase shift of the carrier, there is no phase shifting which is happening in DPSK, so this is not also the correct. More protection is provided against. No, this is not also correct. So the correct answer will be A. Okay, so differential phase shifting is not coherent version of PSK. It is differentially coherent modulation method. So there is no need for synchronous carrier at the demodulator. Okay, so that's the point. So that's in 2 mark they have asked. And we'll see the problem related to DPSK in here. Okay, so here they have given the binary data bits. So 0, 1, 0, 0 they have given. And here, as you can see, as I have told you, they give you which type of universal operation that you have to perform. So in here they have given you have to delay and XOR the DPSK signal for transmission. Okay, assuming, and also reference bit also given in here as 1. Okay, and after that assigning phases. Logic 0 means you have to assign pi, logic 1 means you have to assign 0 respectively. So as the result, we have to find the phase of the DPSK signal. Okay, so out of this 4 option, one will be the correct. We'll see that how. So as I have given in the question, we're going to use the XOR, and this is the truth table for XOR. So same bit means you'll get output as 0. We got a different bits means you'll get binary output as 1. Okay, and the logic operation Y is equal to A XOR B. So this is the constructed diagram. Okay, as you can see, here we got input data that is given in question. This is the bit stream one by one that we're going to enter, and that you're going to delay it, and then you're going to perform XOR, and after that you'll be going to see the phase of that XORed outputs. Okay, so we'll see that now how. So, and remember, reference bit is also given as 1. Okay, so here logic 0 means pi, logic 1 means phase will be 0 phase. Okay, so as you can see, we got a data. This is the data which is given in the question, 0 1 0 0 1, and reference bit here we have taken it as 1 in here. So just you have to XOR it. These 2 outputs that you have to XOR. 1 XOR 0 will be 1. Okay, and then 1 XOR 1 will be 0. And then 1 XOR 0 will be 0. And then 0 XOR 0 will be 0. 0 XOR 1 is 1. So as a result, 1 means you have to add up 0 degree, and 0 means you have to add up. Okay, so here I have changed it wrongly. Okay, so this should be pi, and then 0, and then pi, 0, 1 minute, it is pi, and then 0, and pi, and 0. Okay, this is the correct answer. So out of this option C is the correct one. Okay, so if you read out it, option C will be the correct one. 1 minute. Okay. So in the same manner, we'll see the question here. Instead of XOR, we have used XNOR. Okay, the same pattern, and you'll get the output. Okay, so first 2 bits are given. So pi is given. So out of that, once you perform the operation XNOR using this truth table, you'll get the same answer in here. Okay. So that's it. That's about DPSK. So now we'll see QPSK topic. Okay, so the formulas related to QPSK. So for QPSK, I'll project it first. So for QPSK, we're going to use 4 bits. Okay, so we're going to take 2 bits. So in Bpsk, for a single bit, we'll take a separate carriers. Okay, so for logic 1 means along with carrier 0 degree will be added. Logic 0 means 180 degree will be added. So for a single bit of TB, we'll use the separate carrier. But in QPSK, we have to club of 2 bits. Okay, TB is the bit duration. 2 bitsly we're going to group it. Okay, so that's the first point which says, and as you can see, depends on the data. Logic 0 and logic 1s, we're going to change the carriers. Okay, so here as you can see, it involves 4 different types of phase shift keying. Okay, so why in the sense, so as you can see, 0 0 will be for the data, you have to add up 0 degree for the carrier. If the data symbol is data, TB is single data binary bits. Okay, so once you combine that data into 2 bits means that is called symbol duration TS. Okay, so this will be a single bit duration, this will be the single bit duration. And as you can see, 0 0 means 0 degree will be transmitted, 0 1 means 90 degree, 1 0 180 degree, 1 1 means 270 degrees respectively. So in this, with the help of the diagram, we'll see that now. Here we got the data 0 0. We have to change the data with 0 degree. Carrier should be add with 0 degree. So 0 degree waveform will looks like this. So this is for 0 and this is for the second data bit 0. And next for 0 1, as you can see, 90 degree. So sin theta plus 90 will give you cos theta. So in betweenly, as you can see, we have formed it. So 1 0 means 180 degree. That is opposite of this sine waveform, a mirror image, and 270 means inverse of this carrier waveform. It was, so as you can see, 90 degree means the shape will be in W, inverse means that in shape of M. Okay, so in between, one disadvantage in QPSK is there is a discontinuity of modulated waveform. As you can see in here, there is a discontinuity. Here also there is a discontinuity. So that is one type of disadvantage in here. So by making the connection, as you can see, there is a discontinuity. That's one type of disadvantage in here. And the QPSK are of 2 methods. Okay, so we can design a transmitter using 2 methods. So one is called offset QPSK and second one is non-offset QPSK. So first we'll see, this is the diagram, transmitter diagram for offset QPSK. Offset means the basic function of QPSK is, here you got a binary data. So 0 1 0 1, this is the data, we'll name it now. So next step, we got a demultiplexer. What is the function of this demultiplexer is, it will separate odd data and even data. Okay, I channel, in Q channel it will separate it. So as you can see, we'll name the positions in here, 1 2 3 4 5 means all the odd data, that is 1 1 1. So all the 1 data will be taken out separately and all the even data will be taken out separately. And as you can see, after that even data that we have taken as input, you have to introduce a delay. So because first we're going to take odd, after we're going to perform even, so we need to introduce a delay in here. Okay, so once we got the odd data separately and even data separately, then using the carrier, odd data means you have to multiply that with sine, even data means you have to multiply that with cos term, cos signal. Okay, cos carrier. As the result, you'll get odd number of modulated data and even numbers modulated data. So by adding it up, SO of t and SE of t, you can form the QPSK of the output. And that is for offset QPSK. And what is non-offset means, you have to remove the delay. Simply directly both will be parallelly taken out separately and you can perform the modulation operation. So that is called non-offset. Okay, so we'll see the constellation diagram in here, and for this is the equation. So VQPSK of the mathematical equation root 2 PS amplitude and power term cos of omega CT. In here only we have changed the symbol, that's why it is called phase shift keying. And here we got an equation 2m plus 1 of pi by 4. By substituting here we are talking about quadrature. Quad means 4. So here you have to substitute m is equal to 0, 1, 2, 3, and while substituting m is equal to 0, you got phase shift that differs with 45 degree. Okay, so and while you are substituting m is equal to 1, you got a 3 pi by 4, and the difference between, as you can see in this phasor diagram, how equally these are the datas, okay, and how it has been placed equally means with the separation of 45 degree apart. Okay, so and then 3 pi by 2, and then 5 pi by 2, and then 7 pi by 2. In this manner we have divided. Okay, so as the result, this is the phasor diagram for it. So this is 5 plus and minus cos, and this is the plus sign term, and here you got minus sign. So this will be the reference term in here. And as you can see, once you substituted it, you'll get this equations for B of t and BO of t. So this is the first quadrant, second quadrant, third quadrant, and fourth quadrant. Regarding to that, you can substitute and expand this equation. So in that quadrant only, you can place the data 1, 1, and here at the quadrant 2, that you can place data 0, 1, and at quadrant 3 you can place the data 0, 0, and at quadrant 4 you can place this data with an equally placed. Okay, not only in terms of square that you can draw, using the circular constellation also we can draw. And the formulas, power error, probability error formula, energy formula, and bit error rate for QPSK. Okay, so there is only one problem that is asked in QPSK in the year of 2004 that we'll see now. Okay, so a source produces binary data at the rate of 10 kbps. Okay, so what is kbps is how speedily the data it travels. Okay, so and that is RB, and RB is given in here as 10 kbps. So the binary symbols are represented as shown in the diagram. Okay, so this is for binary, and here we got two different cases. Okay, so the source output is transmitted using two modulation scheme. So one is Bpsk, another one is QPSK. Let B1 and B2 be the bandwidth requirement of the rectangular pulse is 10 kHz. B1 and B2 are, so they're asking to calculate bandwidth for Bpsk and QPSK. Okay, so that we're going to see it now. So out of this 4 options, we got the correct answer is C. That we'll see now how. So the required bandwidth for M-array PSK, a common, it's not about 2 or 4 or 16, a common formula for M-array PSK is bandwidth is equal to 2RB by N, where M is equal to 2 power N. Okay, so N defines the number of bits that we're going to use. So for Bpsk, we have used one symbol. Okay, and for QPSK, we have clubbed datas into to form a symbol, right? Bits into symbol. So N is equal to 1 and N is equal to 2. So as you can see in here, for Bpsk, M is equal to 2 power 1. So that is once the formula is substituted. Okay, so with the help of this, we can substitute the formula using this, that is 2RB divided by 1. RB is, that is given in the question, 10 kbps. So we can substitute 10 into 10 to the power 3. So final answer will be 20 kilohertz. And for QPSK, the formula is M is equal to 2 power N. So that means you have to substitute 2 power 2. So 2 power 2 is 4. So once you got the value for M, you can use the same formula by substituting N in here. Okay, so as a result, you got the combination of data. B1 is equal to 20 and B2 is equal to 10. 20, 10. So the answer will be C in here. So the correct answer is C. So that's about QPSK. So next topic that we're going to see is M array. So Bpsk for data that we have taken, bit duration symbols are TS is 1, QPSK, DPSK it's an advanced version of QPSK. There is no separate need for carrier. Whereas for QPSK we have clubbed two bits to form a symbol TS. Okay, so M array means M number of data that we can form a group, we can form a club. It may vary, the data is like 4 PSK, 8 PSK, 16, 32, 64 in this manner it will get to vary. Okay, that's why it is called M array PSK, and the formulas related to M array PSK we'll see now. Okay, so as you can see, QPSK is a special case of M array PSK, where in QPSK we have taken pi by 4, right? We got 4 data, constellation data like 0, 0, 0, 1, 1, 0, 1, 1. But in here for M array we are going to take the value as M in here. Okay, so as you can see, M ranges with 2 power n. Okay, as you can see the constellation diagram, the symbols ranges from S1, S2 up to Sm minus 1. Okay, so and the difference, the space between the first data and the reference line is pi by m in here. And second difference, so from here to here will be, the second difference, the gap between those two symbols will be 2 pi by m. And the energy from the center point to that zero origin to the distance, and the energy will be calculated using root ES into root PS TS. Okay, so this is the constellation diagram for M array PSK. Okay, as you can see, the points are in a infinite number of times that you're going to mark it. Where in QPSK we got only 4 points, whereas in BPSK you got only 2 data, logic 1 and logic zeros. Okay, so and the formulas related to it, I will see that now. I'll project it. Okay, so as you can see here we have taken a minimum number of points, okay, to get the easier concept to calculate distance. Okay, the distance between D. So as you will take these two data's gap and will calculate the distance. D is equal to Euclidean distance. Okay, so and the center point between those 2 points is called X, and the angle difference from this point to S2, that we can take it as 2 pi m. Okay, so theta is 2 pi m. And sine of pi by m, so this angle now we're going to calculate. So this triangle that we're going to calculate the distance. Okay, so as you can see, sine of pi by m is equal to distance between S1 to X and 0 to S1. Okay, so the corresponding value in here is that we can take it as S1 to X value is D by 2. Here we got total distance is D. So in that half value will be D by 2. So we'll take it as D by 2. And 0 to S1, as you can see, the energy value is called 0 to S1, 0 to S2, that is root ES. So we can take this value is also root ES. So as the result, sine of pi by m is equal to D by 2 root ES. So it's very important formula. In distance calculation, they'll ask you using a problems. Okay, so D is equal to, once you take D onto the other side, other terms will becomes 2 root ES into sine of pi by m. Okay, and as you can see, the difference between BPSK and M array FSK here I have showed. So logic BPSK we have taken a separate logic datas, and for separate datas we have used the carrier, different carriers that we have used. One means we got a number of cycles are more in manner. Okay, so for logic 0 means number of cycles are lesser. Whereas in MFSK for 4 level means 2 bits that we have to group. So for a single data we got one carrier, and here as you can see that we have grouped, and 0, 1 that has been grouped into a single symbol, and for that you have to use a separate carrier. So 4 different types of carriers are used for a 4 level of M array, MFSK. 4 FSK we have used 4 different types of carrier, as you can see in this diagram. Okay, so that's the same concept in here as well. For BPSK we have taken a comparison for MPSK. Okay, so here we take an FSK means different frequency, PSK means different phase that you have to add up. And power spectral density formulas, bandwidth formulas. One more important formulas that you have to remember is the bandwidth efficiency is FB by B. Okay, so the formula will be log to M. So there is two problems that they have asked using this formula. I will try to solve it now. So in 2014, there is 4 sets. In set 4, there is a question related to M level of PSK. So I'll read out the question. An M-level PSK modulation scheme is used to transmit independent binary digits over a bandpass channel with bandwidth 100 kHz. So bandwidth is 100 kHz and bit rate is 200 kbps. The system characteristic is raised cosine spectrum with 100% bandwidth. Okay, so minimum value of M is what they're asking. What is the concept is the whole communication system for using BPSK they have given. So the whole system which consists of transmitter, channel and receiver. Okay, so here at the transmitter side we got a bit rate of 20 kbps speed. The data is going to pass in the band pass channel. So band pass channel means only particular frequency alone will get to pass through. That is called band pass channel. And the bandwidth for it is 100 kilohertz. So as you can see, the designing of the channel will be done using a filter, and the type of filter here we are going to use is called raised cosine filter. Raised cosine filter characteristic, I'll show it in here. As you can see, this is the raised cosine filter. So this is the time domain characteristic of that filter, and here you got frequency domain which ranges from 0 to alpha. And as you can see, the based on this alpha, that is the raised cosine roll-off factor, based on this roll-off factor you can extend the limits. Okay, so based on this roll-off factor only you will get the corresponding response of that filter. Okay, output of that filter. So imagine it's like a gate. Okay, so in that gate the opening of that gate have to be determined, right? So that gate opening size will be determined using the alpha roll-off factor. So in some cases they'll use a symbol for roll-off factor as or in some cases they'll use like a formula alpha. Okay, so and the formula for multi-level PSK, the formula just I have showed in here. So 1 plus alpha by log 2 L into R. So the correct answer is option is not given, so we'll solve it in here. So the bandwidth requirement for MRA PSK is 1 by T of R is we can take it as 1 by T. So 1 by T of 1 plus alpha. And as you can see, once you substitute 1 by T of 1 plus alpha in here is 100%, that is given in the question. So 100 into a bandwidth that you have to write. So we can write it as 100 into 10 to the power 3, the bandwidth for the requirement channel. Okay, so as the results, once you equate the formula along with the given data in the question, for alpha is equal to 100%, you can get 1 by T of 2 is equal to bandwidth, that is 100 kilohertz. So from that you will get the value for T. And bit duration can be calculated using the value of 1 by 200. So this value, so bit duration RB can be calculated. Okay, so TB can be calculated out of the RB. So RB is equal to 1 by TB. So from this we can inverse it, you'll get the value for RB here. So the total formula will looks like this. So simple duration divided by log 2m. So log 2m can be calculated out of it. So the value they are asking the question is m. So from this we can get value for m is 16. So answer is m is 16 in here. So an important problem in MRA PSK that we'll see now. So they have given two diagrams. Okay, two constellation diagram are given for 8 PSK. Okay, so as you can see, for a single question statement will be given, single diagram will be given. From this diagram, like a linked question, they'll ask you. Here the linked questions are 21 and 23. Once you got the answer for 20, you have to use that answer to solve 21. So we'll see that now. So for a constraint, the minimum distance between D is, we're going to calculate it now. D and also how that D is related with R. So once you find R1, you can calculate R2 in here as well. Okay, so for both R1 and R2 radii, that we're going to calculate now. So we'll solve that problem. So a 4-phase signal constellation, the first diagram that is taken in here, R1 that we have taken, and distance formula we already know, D square is equal to R1 square plus both the distance are in here are R1, so we can write it as R1 square plus R1 square. So D square equal to 2R1 square. As the result, we got R1 equal to D by root 2, that is 0.707 D. And similarly for R2 also we have to calculate, and the distance is using this cos law that we can calculate. So D square is equal to R1 square plus R1 square, minus 2R2 square of cos pi by 2. So out of this you can get the value for R2 in here. So now we got R1 and R2 value. R1 is 0.707 and R2 value is 1.3065. That you can round it off to 7. So the correct answer is D in here. And from this D value we're going to use and solve it. Okay, so 21 question is, assuming a high SNR, all signals are equally probable, the additional average transmitted signal energy required by a 8 Psk signal, okay, to achieve the same error probability. So probability of error they're asking to calculate. So as you can see, we'll solve it now. So here equally probable means all the points that we have placed in a equal manner and the energy is root Es. And power SNR can be calculated for the first constellation, second and minus first, that is 10 log of Es by that signal power by noise power. So as the result we got the radius value. Once you take and convert it, you will get SNR as 5.33 dB. Okay, so that's it. That's about the option D is the correct one. Similarly, one more problem is there in related to MRAPSK. We'll solve it now. It's a very important problem that is also similar to QASK as well. So we'll solve it. So this is the question that is asked in 2007. So a 2-4 array signal constellation are given. Okay, so 2-4 array signal constellations are given. Phi 1 and Phi 2 both are orthogonal. Both are so in the same channel you can transmit two different types of signals. So that's the property for orthogonal or orthonormal. So assume that 4 symbols in both constellation are equally probable, and N0 by 2 is the power spectral density of a Gaussian white Gaussian noise. Okay, so here first we have to find ratio or the average energy of the constellation 1 to the average energy of constellation 2. So for that, first we have to calculate energy for this constellation diagram, that you have to divide with the energy of this diagram. Okay, so we'll see that now how we can calculate. So as you can see the energy for this, so the distance, the coordinates first we'll write it. So here the coordinate for this point will be 0, 0, and for this we got 0, x is 0 and y value will be you got plus root a 2a, and here also in this manner you have to write the corresponding coordinates. As the result, the first value, so distance once you calculated 0 minus 0, it will give you 0 square, and then here you got a 0 minus root 2a. For this distance value is, you can write it as minus 2a square, and similarly for this distance and this value and this distance value that we have taken in 4. Okay, so as the results, once you square it up and sum it up, you'll get the value as 16a square energy for the first constellation diagram. And energy for the second constellation diagram, once you again both are equal values, so you can write it as the final answer will be 4a square. So in first option they have asked you to divide energy of constellation 1 and energy of constellation 2. So 16a square by 4a square, which will give you 4. So the answer for this is option B is the correct answer. Okay, so now we'll see the last problem related to it. So as you can see, as a continuity of that, it's a linked question, right? So 58th is, if these constellations are used for digital communication over AWGN channel, then which of the following statements are true? Okay, so first one is the probability. Remember, out of this question, for constellation 1 is got the higher value and constellation 2 got lower value. Okay, so just remember, probability of symbol error for constellation 1 is lower and probability of symbol error for constellation 1 is higher, and probability of symbol errors is equal for both constellations. Obviously both are not equal, so you can delete it. So either answer will be already projected it. Anyway, we can skip out the unwanted answers. Okay, the value of N0 will be determined. So N0 is a noise probability density function, will not get to change. Okay, so this is also will not be the correct. Either we can say option A or option B. But with the help of that energy, which one is higher? Constellation 1 is higher. So which means you can say option 1 is the correct one. Okay, so probability of error will be lower for constellation 1 because of the higher energy. Okay, so that's it. That's about MRA PSK. Last topic is QAM. So we'll quickly finish it off with the digital modulation and will be over. In next class we'll see Shannon-Fano and Huffman related problems. Okay, so as you can see, for QAM it involves both amplitude varying and phase varying. That's why it is called QAM, and or else it is also known as amplitude shift keying. Okay, so in the constellation diagram for 16 QAM, this is the constellation diagram. Okay, and distance will be calculated. Just now only we have solved a problem, right? So with the help of that we can calculate the distance. So distance between the points are d is equal to 2 root 0.1 es. So similarly we can calculate the energies. Once you calculate, we can calculate the distance as well. So es is equal to 4b in here. Okay, so this is for 8 QAM, so which got 8 points. So previously we have seen for 16 QAM. Okay, so and the bandwidth formulas, and as you can see, we'll see the question, only one question that is asked under QAM, that is in 2003 they have asked. So a bit rate of digital modulation system, communication system are, okay, so modulation used in here is 32 QAM. The minimum bandwidth that we have to calculate. So for ISI without interference and with minimum D-min that we have to calculate. Okay, so in an ideal Nyquist channel, bandwidth required for the formula is RB by 2. Okay, so for 32 means you can take Q is equal to 32, so 2 power V is equal to 32. Q is formula is 2 power V. So out of this we can calculate V is equal to 5 bits. So from this RB can be calculated by dividing R with 5. Okay, so out of this we can take and substitute this value. As you can see, RB by 2, so R by 10 kilohertz, that you will get. So option B will be the correct answer. Okay, that's it. So all the digital model